cost. And in order to reduce cost, then we said that, well, let us do modular design. In other words, you take copies of just one bit full adder and connect them in series to implement multi-bit adder, right? And as a result, because of the serial connection, one of the main issues that arises because of the sequential nature of the carry propagation, so it incurs delay. So as you can see that there is always a trade-off between this cost and delay, and the main issue of adder design is to make a proper compromise between these two parameters, or these two objective functions. Now, one of the challenges in adder design is to consider that how fast you can generate the carry in a reasonable time and in reasonable cost. Okay, and that's why you were talking about different solutions like carry look ahead. That means we try to generate carry ahead of time instead of waiting for the carry to arrive, right? But it has pros and cons, as we have seen, that the cost again becomes impractical. And there are many other proposals like hybrid architecture for address, mixing carry look ahead as well as repo carry and so on. And there are other proposals like carry select, carry look ahead tree, and so on. So in particular, we'll focus on few more architectures that is based on the some kind of that resembles some kind of tree, because as you know that in case of a tree, a tree has an interesting property that its depth is logarithmic in the size of the nodes, and therefore if the structure resembles a tree, then you can reduce the delay to it. I mean, the delay of transmission may be of logarithmic order, right? So there are many proposals based on this tree architecture for adder design. So we look into that one by one. And so I'm going to present before you solution 4, which is a tree-based adder. The adder carry look ahead tree CLT. That's also some kind of tree-based adder, but there are other important and nice architecture which are also based on trees that we will discuss now. Okay. Let us first recall that our 4-bit CLA, because that describes very well that the cost of the architecture as well as the delay propagation. So you know that in case of a carry look ahead adder, the entire design is based on the recurrence relation, right? Which tells you what would be the carry of ith stage in terms of the previous carry, right? Okay. So ith stage carry it depends on GI plus CI plus PI, and GI, PI, those are simple functions of the input, right? So this is the fundamental carry recurrence relation, and using this we can write Boolean expression for different carry functions, and those carry functions have to be implemented in hardware, right? So let us re-examine this process once again and see whether we can observe any such pattern there. All right. So consider a 4-bit carry look ahead adder. We have seen this example many times, but let us go through this once again. And we observe that in carry look ahead adder, this carry logic cost grows, is of the order of n cube for n-bit adders, right? And that's why this whole business of reducing the cost without compromising delay as far as possible. Well, so remember these equations. I say it is a 4-bit CLA, so I have C1, C2, C3, and C4. C1 is generated here from here. So this is G0 plus C0 P0 and so on. Keep on expanding this, right? And we know that this G's and P's, these are fundamental functions of input. So what do you observe this? From these equations, in our previous classes, we observed that, so there are cubic terms, right? Because there are n square entries, and each entry may be, the length of each entry may be of the order of n, right? It's keep on increasing. If this happens to be Cn, then this term will be, there will be n terms here, right? N plus 1 terms. Okay. So what pattern do you observe here? That is very important. I mean, is there any pattern which you can utilize so that you can come up with an efficient design? Okay. So first of all, let us look into these terms and see whether we can find something interesting here. Okay. So look at this term. So this is the product of all these p terms, right? P0, P1, P2, and P3. Okay. So if I have Cn, the nth carry, in case of an n bit adder, so then this term will grow as P0, P1, P2 up to Pn minus 1, right? And this is the most complex term in this entire, if you look into all these expressions, this is the most complex term here, right? This is the largest term. Okay. So what do you observe here? There are other interesting properties. See, look at the previous term. So this is a substring of this one, right? Because this is P0, P1, P2, P3. This is P1, P2, P3. So this term is a substring of this, right? Similarly, so this is a substring of this, and this is a substring of this. So that these p terms are gradually being concatenated with the newer variables, right? So in the horizontal direction, there is a growth of terms like this, right? Similarly, if you look into this diagonal direction, for example, here, across different terms, so you have P0, P1, P2, P3, you have P0, P1, P2 again. So this term, this is the last term of the previous expression. So this is a substring of this one, right? And also you observe here. So this is P0, P1 is a substring of this, is a substring of this. And similarly here, right? So as you can see, so both in the diagonal direction, also in the horizontal direction, there is a growth of terms, gradual growth of terms. I mean, there is a property, there is a substring property which is satisfied, right? For example, so if you look into this this series of terms here, you have P0, then you have P0, P1, then P0, P1, P2, then P0, P1, P2, P3. So if we have Cn, what will be the last term here? P0, P1, P2, P3 up to Pn minus 1. Diagonal terms, what do you observe? Have you seen any such sequence in some other areas of computer science? So let us forget about adder design for the time being. Let us look into a more fundamental problem here. Are you familiar with this sequence of terms like this, which grows one by one like as a substring? Anywhere in computer science have you encountered this kind of thing? So in general, this problem boils down to, suppose this P0, P1, P2, P3, these are my inputs, and I want to generate these product terms, or this set of product terms from the input. What would be the most efficient way of generating these terms? And this is a general problem. Like, for example, when you consider P0 times P1, here this operation is a logical AND operation, right? But in general, this could be anything. This could be a binary operator. It could be a general binary operator. Maybe, I mean, this may be a logical AND function, logical OR function. It may be an arithmetic addition function or multiplication function, doesn't matter. It may be a general binary operator between two elements. Then the problem is, given P0, P1, P2, P3 up to Pn minus 1, how do I generate this sequence of terms? P0, P1. So these terms are growing one by one.
But is this a problem which boils down to divide and conquer?
Well, but this is in computer science. This problem is we can do divide and conquer in order to implement it, but this particular problem has a name in computer science. This is called prefix sum or prefix product problem. Because see, this is the prefix of this, right? I mean, this term zero. This is the prefix of this. Similarly, P0, P1 is the prefix of this. P0 is the prefix of this. So there is a sequential prefix property, right? So, and this operator in this, I mean, for this particular example, this is logical AND, but it could be a logical sum also, it could be a prefix sum operator also, or maybe arithmetic addition, multiplication, doesn't matter. So in general, this is called the prefix sum or prefix product problem. So this is a fundamental problem in computer science, and it appears in many other places, as we will see later on. So the question is how to compute efficiently in reasonable cost and time this sequence of terms. Okay, so let us forget about P0. So I'm just writing the general problem here. So this is the prefix product problem. So I want to generate this kind of term, x naught, then x naught x1, x naught x1 x2, and this keep on increasing one term at a time. I mean one variable at a time, and finally this. So my inputs are x0, x1, x2, x3 up to xn minus 1, and my output should be this one. So how should I proceed? What is my algorithm to generate these terms efficiently? So if I can solve this problem, this is the same problem of generating these carry terms, right? Because in the Boolean expression of the for the carry bits, so we have similar patterns in the diagonal direction, also in the horizontal direction, right? So now forget about hardware. Now the problem reduces to a combinatorial problem, which is the problem. This is known as the prefix sum or prefix product problem. How to generate prefix sum and prefix product efficiently from inputs? That is the question. So this entire problem of efficient adder design now boils down to solving the prefix sum or equivalently the prefix product problem. Now it has a very brilliant solution, but and amazingly simple that I'll present before you. And not only that, you may observe that this diagonal prefix property is also present if you look into the other diagonals, like parallel diagonals here, same thing. P1, see, it starts with P1, then P1, P2, again P1, P2, P3, and so on. So this is a repetitive pattern, Similarly here, also prefix property, P2, 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 P3, and so on. Now imagine that you have C1, C2, C3 up to Cn. So you can identify many such diagonals, right? These parallel diagonals, and each diagonal, the terms appearing along each diagonal happens to be a prefix sequence like this, right? And similarly in the horizontal direction. Okay. So if you can solve this theoretical problem, this generation of the prefix sum and product from the inputs x0 to xn minus 1, we are done, right? So here this is a brilliant solution, but very simple. Okay, so the basic idea is the following. So this is my input. For example, let us start with only just 4 variables. So x0, x1, x2, x3, and I want to generate terms like this. What would be the prefix sequence? x0, then next term would be x0, x1, next term would be x0, x1, x2, and the other term, last term would be x0, x1, x2, 2 and 3, right? All product terms. Okay. So I can do one thing. I can take the product of these two guys. So I generate x0, x1, and then I can take product with this guy. Then what would be the naive approach? Take x0 is straight away available. Then take the product between these two guys. You have x0, x1. And once you have x0, x1, then you take product with this guy. You get x0, x2, product of these 3, and then finally take the product with this, So what is great in it? You just keep on taking the product sequentially. That's done, right? But then in order to generate all these product terms, these 4 product terms, you can see this is somewhat again linear in time, right? Because you are taking the product of these two and then taking the product with the third term and with the fourth term. So there is again a sequential nature, right? So our main objective is to reduce the delay. So a linear time solution is obvious, right? Because if you look into this previous, so linear time solution is, so you just start with this and then I take the product with x1 and then I take the product with x2 with the previous one, keep on taking the product and generate the sequence, right? So that means you have n terms here. So I do n product operations serially. So what is great about that? Can you do faster? That is the question. So serial computation of the product term, the prefix terms, that's obvious, right? That's trivial. Keep on doing, yes, that's trivial. So can you do faster? Now forget about your adder business. Just think about this from a combinatorial point of view. How about this? Suppose you do take the product between these two and take the product between these two, similar kind of thing, Okay, let us visualize this thing this way. Let me show you this diagram. Okay, let us do this way. Assume that these are just signal lines or that data moves along this line. And suppose this is the product operation. This star represents the product operation. And this red dot that represents just flow of data. I mean, in terms of hardware, you may think that this is nothing but the fan out. So assume that this is an AND gate. If my prefix composes of this logical AND operation, or this may be a logical or it may be an arithmetic addition or multiplication, does not matter. It's a binary operation. So here we get straight away x0, right? Here, what do we get? So there is a product operation here. So we get x0, x1, because x0 appears here, and this is a 2-input AND gate. Okay. So you get x0, x1 here. And then this result, this x0, x1 is being fanned out here. You take the fan out here. So this is again an AND gate. So it is multiplied with x2. So you get this term here. And you fan this out here. So this becomes, this carries signals x0, x1. And this in this line, this is already computed x2, x3 because of this AND operation. You take another AND operation and you finally get this, right? So is it better than the serial computation? What would be the serial computation would have been like this, like signal flow like serially like this, right? But here we have improved the delay a little bit, isn't so? Do you get the idea? How about if I just want to expand this to x0 to x7? Look at this diagram. Is there any confusion here? So I want to expand this to x0 to x7. Divide and conquer. So what to do? Look at this diagram and you would be able to give the answer. Hmm? See, you have used this kind of technique many times in elsewhere, I guess. You have solved this half the problem, and then you have to expand this for the other half. Now my input is x0, x1 up to x7. So there are other 4 literals, x4 to x7.
Hello,
Huh?
sir.
Yes.
Sir, we repeat this same thing again and make a connection from x3 to x4 and x5.
Exactly. Brilliant. That's what I was waiting for from you to hear. Yes, correct. So you repeat this thing. So this term will be, they will run from x4, then x4, x5 up to x7 here, right? Similarly to this. And then we have to multiply with this, with the prefixes of this guy, right? So this is the final product term here. So all I need to do is to create a fan out from this point and use AND gates here, right? You are done. So if my input space now, from x0 to x7, then I can generate all these prefix terms, x0, then 01, then 012, up to 0127, right? And in this process, I have done certain operations, and these are my binary operations, which are represented as star. This may be I mean, if you think in terms of hardware, this may be considered as AND gate. Now, if you think in terms of a algorithm or a program, this is nothing. This is just a binary operation, right? And in terms of hardware, this is a fan out. And in terms of algorithmic way, it means that this data is being used 4 times here. That's it, right? So if I design this structure, so what do we see here? What is the cost, delay, fan out? I mean, from hardware perspective, these are the parameters, right? What is the cost? The cost means, how many AND gates I am using here. And this fan out, fan out is important from hardware point of view, because when the fan out increases, the delay increases, the cost increases, and so on. And also and the most important thing is the signal delay, because when you want to design this carry look adder, my primary objective is to reduce the delay, right? I mean, if we want to generate this prefix term serially one by one, then the delay is linear. But if you use this architecture, this kind of structure, so what would be my cost, delay, and fan out? When the inputs run from 0 to n minus 1, I have n input variables here. This is a very nice structure, right? And recursively you can build. Now, if I have 16 variables, I can repeat this whole thing and do this, keep on doing this, fan out and so on. So please tell me what should be if I have n variables at the input, what should be my cost? What is the cost, delay, and maximum fan out?
So maximum fan out will be n by 2.
Yes.
So delay will be of the order of log n.
Correct. And cost? What is the depth of this network? I mean, as you said, the delay is log n, so the depth is logarithmic, right? And
Yes.
Look at each row. How many AND gates might appear? You look at the
N.
rows, right?
N log n, order of n log n.
Right. So you have already got the correct answer. So delay is logarithmic, right? Because of this recursive structure. But the fan out is of the order of n, right? Because we are duplicating this fan out I mean, when I duplicate this structure, this fan out keeps on increasing, and the final fan out will be n by 2, so it's of the order of n, right? And the cost is n log n, right? Okay, but as far as the delay is concerned, now I have been able to achieve logarithmic delay instead of the linear delay, right? But at the cost of a little bit cost, not too much. So we're in a good shape now. So having solved this fundamental problem, so now you can look into this carry generation problem once again, and this idea leads to many tree-based adder architecture. And one of the famous architecture is the Brent-Kung architecture. So first of all, so they tried to see whether, this fan out n, this is still a problem, because this high fan out is not acceptable. So whether you can reduce this fan out without compromising the delay. So that was the next challenge. And
so is fan out a bigger problem or fan in? Because in the sense that we cannot have a n input adder for arbitrarily large n, n input AND gate for arbitrarily large n, but fan out may not be that bad also.
yes, a fan out is also a problem, because if fan out means what? This output of the gate that has to feed so many inputs, right?
The power problem.
Yes, so they have to supply that current, the current needed. So the power increases, right? Yeah. And both fan in and fan out, both are problems. Both create different types of problem. And moreover, whenever you have fan out, so many gates are, these gates are connected, they're from the common point, right? So the capacitance of this node would increase significantly. And therefore, whenever there is a logic change or switching from logic 0 to logic 1 or 1 to 0, those capacitors which are inbuilt, inherently hidden there, they have to be charged and discharged, and that would take longer time. And it would badly impact the delay. So this fan out of the order of n for large n, this is not acceptable. But theoretically, it's a very nice solution. I mean, if we disregard fan out, then it has a very nice reduction in delay, as you can see, with reasonable amount of cost, isn't so? N log n. So as you can see, this is a basic fundamental computer science problem. You will see this application of this problem in many other places later on, and it has close connection with the hardware design as well. These two problems are identical. Okay, that is the message I want to give it to you. Well, so what is the engineering solution of that? So the next solution is based on this prefix tree, but with little bit changes, and that is, so this is my input, and this is my output, and the basic idea of prefix tree is to create this recursive tree structure so that the delay becomes logarithmic, at the cost of n log n, but maybe in this simplistic form, this fan out is still a problem. Well, okay. So let us see whether you can improve this fan out, and this is what is done in Brent-Kung architecture. It's more or less the similar thing, but with a little bit modification. So as before, here the symbols are a little different because I have taken this slide from other source. So this is the AND operation. So these yellow circles, they represent this AND operation, and this is fan out as before. So as before, you have to do this kind of thing at the first level, and then at the second level, you are making the jump. Okay, a similar thing as in the prefix tree. This, but you use some kind of these nodes. Some. I mean, if you look into the previous one, here. So what is going to do that? I'm going to use some extra nodes. See, the cost is n log n here, right? So even if I have more components here, the cost would not have increased, right? Isn't so? Because there are many columns which are already vacant. So can I use some extra components without compromising the cost, but the fan out problem is then solved. So That was some kind of idea. So it is almost a similar structure, but it is a little bit different. By adding some this yellow circles, there are more addition of this yellow circle, but still the cost remain logarithmic. And in doing so, this fan out can be reduced to logarithmic also. As you can see here, this is if I have 16 inputs running from 0 to 15. So we observe the maximum fan out in the previous case, we would have observed here, right? At the line X7. In the previous case, it would have been n by 2. But here now observe that this fan out goes to only at this binary levels, Yeah, so I mean, using some this yellow circles judiciously, it is possible to reduce the amount of fan out. As before, this represents AND gate and this is fan out. And we have the same kind of recursive structure, but with slight modification. And as before, you can see that this line will generate X0, the next line would generate 0, 1, and the third line will generate 0, 1, 2, and keep on generating this prefix product one by one. So it would generate this. It has the same input and same output. Basically the structure is also the same, but there is a little bit judicious reuse of these blocks so that this fan out is limited. I leave it to you to please examine this structure a little bit more carefully. You will see this this fan out would be logarithmic, Yes, I made a mistake here. Here this fan out should be log n. Yes. Sorry. Okay, I'll make this correction later. This fan out should be log n. Okay, now let us re-examine that. This is about this prefix generation, right? Like if we have this x0 to x15, and then you can generate this prefix sum, and the cost is so far n log n that we have seen, right? But what about the adder cost? Okay, so let us go to the previous slide and see this slide again. So far we have the prefix means if we look into these diagonals, right? So P0, P0, and then 0, 1, 0, 1, 2, and so on. So far we have solved this one diagonal problem. Just generation of this one diagonal has been solved in cost n log n, right? But how many diagonals you have? If we have C1 to Cn minus 1?
So we have n diagonals.
N diagonal. So one diagonal.
And the common because okay, no, they're not.
Yes. So far we have solved prefix sum problem for the one diagonal, right? So you have n such diagonals, right? So what will be the total cost of this generating all these carries? That was my question here. Let us expand this. Okay, so we observed that previously that cost is n log n for the prefix sum or prefix product problem, right? But we have n diagonal, so then the total adder cost again becomes n square log n, isn't so? Because we have to repeat this kind of prefix tree for n diagonals. Okay. Initially, it looks like that. So we have solved this logarithmic delay problem and the fan out problem here. So I made a mistake here. I will correct that. Fan out would be log of n here. So but still, can we reduce the cost further? Yeah. So that is the question, and that in fact, interestingly, the adder cost can be reduced, and this has been done brilliantly by what is called this Brent-Kung parallel prefix adder. So it achieves logarithmic delay, it achieves logarithmic fan out, and the logarithmic cost for the total adder, full adder, I mean the complete adder. How is it that? Okay, here, this in the previous case, see this arithmetic operation was just a logical AND operation, right? Here, what they did, so this is now a little bit more complex logic module. So this implements this function, this carry recurrence function. Okay. Again, as you can see, this is a simple logic, right? It needs only one AND gate and one OR gate, right? So let us replace those this AND operator by simply this logic module. And suppose your inputs are these G's and P's. Okay, so each module has two inputs. It accepts like this G's and P's. So, and you can see that this is the same structure, what you have seen in the previous slide. But instead of x1, x2, x4, and if you just give this kind of inputs, G's and P's, it will exactly generate this carry signals. So all the carry signals can be generated by a single prefix tree. You don't have to. You don't need n copies of those prefix tree. You got the idea? So this gives you further improvement. And that's what this Brent-Kung parallel prefix adder is. So we reduce this cost to now. The delay becomes log n, cost becomes n log n. Because once all the carries are generated, now you can use independent full adders, right? And fan out is also limited to log n. And this is one of the most brilliant solutions in this prefix-based, tree-based adders architecture. Okay. So as you can see that everything reduces to the fundamental problem reduces to this. Now, if we look back into all this discussion and whatever we have studied so far, you will recognize that this entire, the whole business of carry generation, or the entire carry generation stuff, is nothing but is equivalent to computation of the prefix problem. Okay, and this shows an interesting connection between the fundamental, the abstract problem and the hardware problem. Well, and that's why the theory is important. If you have good theoretical solutions, then it can be implemented in hardware as well. And this, as far as this tree-based adders are concerned, people thought, okay, this fan out, can we further reduce this fan out? Because it's still log n, but can you have constant amount of fan out, but still achieve the same thing, delay and cost? So you see, we are gradually improving. First we reduce the delay, and then we reduce the cost. And sorry, first we reduce the delay, then we reduce the fan out from n to log n, then we reduce the cost from n square log n to n log n. So now the question is, can you reduce the fan out to a constant factor? Say just 2. And that's what is done here. Well, so there is there is a further improvement of this Brent-Kung parallel prefix adder. So they have shown that this cost can further be reduced. It can be made linear, but that I'm not going to discuss in class. That is pretty complicated. Well, so this is an example of full example that if I have a 8-bit adder and I need to generate this C0 to C7, all these carries. So these are this carry generation, the logic this logic, Ci plus 1 equal to Gi plus Cip. So this logic module is shown here, and the whole architecture would look like this. So inputs are this small g and small p's, and so you can see this. The tree structure is hidden here. The depth would be log n. Right? So this is the full example, for 8-bit carry generation. So look at this diagram and so on. So let us now move on to see that whether there are solutions where the fan out remains constant. And here is the one solution, but I don't want to discuss it in detail, but just to give you this information, this is also a very famous adder. This is called Cogstone adder or KS adder. And this is the diagram for 16-bit. These are the same logic modules, but their interconnections are slightly different. The original objective was to make the fan out constant. The fan out is exactly 2. You can see this fan out is exactly 2. And it still, the cost remains the same, delay remains the same. But as you can see, there are a lot of wires you can see, right? There are too many connections. So it increases the wiring complexity. Although this fan out becomes exactly 2, but the number of wires you need to interconnect them, that becomes very high. And therefore the congestion increases, the chip size increases, and again, a lot of difficulty. But anyway, so theoretically, it is possible to do fan out constant. In fact, there are many other architecture based on this, based on trees, but all of them, in principle, they use the same prefix tree concept. But how to interconnect these modules, that determines this fan out and other physical parameters. Well, I think as far as adders are concerned, we will be done with this, but we have one more thing to study in adder. Let us now move on. Okay, so far, we are considering addition of 2 n-bit numbers, right? So 2 numbers are given, A and B. A has n bits, B has n bits. You are adding 2 numbers, right? But in many places, you have to add multiple numbers together, right? Then what can we do better in those cases? Okay, before that, let me tell about what are the overall design considerations when you build hardware architectures. So what are the design considerations? Of course, in the context of adder design, our main objective is to optimize delay, right? So timing. So this is the fundamental design consideration. And then this power and energy, we are talking about this fan out, fan in, and so many things. And if the circuit size increases, your energy would increase, right? And also there is a notion of concept of heat dissipation. This is very important because this is logic circuit. So that means at every, these are outputs and inputs of different gates, right? And in a circuit, there are hundreds of thousands of such lines or logic nodes. They are changing from 0 to 1, 1 to 0 continuously when the system is in function. And whenever there is a transition from 0 to 1 and 1 to 0, they dissipate energy. So the chip becomes excessively hot, right? So you need appropriate mechanism for heat dissipation. You need appropriate logic design technique so that those transitions are reduced and so on. So there are many design considerations like that because it may be a portable system. Then energy is related to the battery life and so on. Power, the instantaneous power is related to heat dissipation and so on. Okay, you need the dissipation of the heat sinks should be appropriately made so that the chip does not overheat it. Okay, and these are determined by these parameters like fan in, fan out, and logic switching, and that's why you are talking about reducing the fan out, fan ins, and so on. And of course, this area or cost, right? And as the cost increases, the area increases, the cost also increases because the yield reduces. The probability of defective chip becomes higher. So all these considerations are interrelated. Area is determined by the size of the logic, the wiring cost, and so on. As you can see here, there are many issues. The logic depth, which determines the timing. fan in, fan out, that determine, this power, energy, and logic switching also. So if there is a logic switching, and if you have high fan out, all the fan out nodes will experience switching. So they are interrelated. Similarly, wire tracks, that how many wires are there, so that will increase the area and so on. So these are the engineering parameters, and these are the different objective functions, how they are impacted. So logic depth impacts timing, as fan in, fan out, they impact power, wiring tracks area impact, logic and wire tracks, they impact area and so on. So while designing adder or in general any hardware circuit, you need to consider this kind of parameters. So that's all about your adder design. Now next we will move on to how about if you want to add multiple numbers. So far we have discussed that, well, we are given two numbers A and B, and we want to add them up, right? But in general, so if you look into if you go to a restaurant, then you see this, there are so many entries, right? So you need to add multiple numbers, right? So one way of doing this, okay, you add these two numbers, you add these two numbers, and then keep on doing this. Again, that means you need to create a tree, okay, right? Because the adders we have discussed so far, the hardware design, that can add only two numbers at a time, right? So if I have multiple operands, what to do? So this is our next concern, that adding multiple numbers. You can do sequentially, of course. You do these two numbers and then add this number to the partial sum, and then add this number to the partial sum, and keep on doing this. Whatever you do by hand, like. Can you do better? You can recognize some kind of tree again, right? I can add this first two numbers, and then I can add third number and fourth number, and keep on doing this, right? So there is an inherent tree structure, maybe you can imagine here, right? In the addition process. That way you would produce, possibly you can reduce the delay, but provided you have multiple copies of the CPU, isn't so? Can you do better? And this is the problem of adding multiple numbers together. And this is what is called the carry save addition. So don't confuse it with, again, like CSA, because we had carry select addition, that's also CSA, and then carry skip addition, that's also CSA. And this is carry save addition. Remember that this carry save addition refers to adding multiple operands. We are given multiple numbers and we want to add them a little bit more efficiently rather than adding them sequentially. That is the problem we want to address now. Okay, so let us begin with a small example. Suppose we have, let us assume that our universe comprises the 4 bits, and unsigned number. Forget about this overflow business and so on. So these are, you are given 6 numbers, and I want to add all of them. So far, whatever design we have considered, so they can perform addition of 2 numbers at a time, right? Whatever design, whatever adder we have studied so far, like ripple carry look ahead, tree adder, whatever. So that means let us take them pairs. So this is the first 2 pair, and this is the second pair, and then this 2 means the third pair, and then I add these 2 numbers, which is here. I add this 2 pair, get the result here, and this third pair I add, I get the result here, and then I keep on adding these results again. So I take these 2 guys and add them together. I have here, and then take this guy here, and this was still left out, and you add them, and finally you get this. We assume that these are unsigned positive numbers, so we are not considering this overflow when I time. just keep on adding. So this is one way of doing this, so far as whatever hardware we have in our possession, right? Because it can only add 2 numbers at a time. So you add them pairwise, getting 3 results, and then add them again in 2 steps. So you have, as you can see, that 1, 2, 3, 4, 5 steps. You have to invoke the addition process, this addition, you have to invoke adder 5 times. Keep on adding this and then move this result here, move this result here, again perform addition, move this result here, and this is still left out. Add this together, this get the final result, right? The final sum. The thing is, can you do better in terms of hardware? So let us think about it in a different way. Normally what we do, when you add these 2 numbers, we take care of the carry, and the carry is added to at the next stage, and keep on doing this, right? Instead, we can do this way. Suppose I add these 2 numbers, we generate the sum, forget about the carry, just just write the sum bits and also write the carry bits separately. So I don't care about the propagation. I have independent full adder blocks only. So they generate a bitwise sum and bitwise carry. And then later on, I will add the partial sum and the partial carry together by some means. Would that work? I do bitwise sum and bitwise carry. So I get 2 strings, and then later on I add those 2 strings. Do I get the same result? You understand the procedure? I don't propagate carry. What I do bitwise sum and bitwise carry.
So in that case, we have to like conserve the extra bit. Like if there is an overflow, then that will cause a problem.
Let us not bother about overflow at this point. Huh? Just think of sum and carry.
So we have to like add, like make join the carry and this sum into one number and then do the final addition.
Like this, you know. So let me tell you this way, you know. Okay. So you have 6 numbers here, right? So I first partition into 2 groups, 3 numbers here and 3 numbers here. Now what I'm going to do is this. Recall that in a full adder block, how many inputs are there? 3 inputs, right? In an independent full adder block, sir, you have 3 inputs. That's why I have chosen 3 numbers here. Now look at this column. So I add these 2 numbers. So this is the sum, and you know I write the carry below. You know. So 110, the carry goes here. So I do separately. You know, that's it. So these are all sum bits. You know. 1, 0. I mean 110, 110, then 2, 1 again. So all zeros. You know. And these are the carry bits separately. So I generate the sum bit and carry bit separately. And then keep on, I have these 4 terms here, right? And then keep on, again I take 3 of them together. And generate this term and again this carry term, right? So now I have these 2 and this is left out. And I again take 3 of them and generate sum and carry bit separately. And then finally I add them, sum and carry, overall sum. So what you can observe that here, all the full adder blocks, they can operate independently. There is no signal flow. All of them are operating independently. Only at the last stage, there is sequential flow of carry. Got the idea?
Yes, sir.
So this is what is called the carry save addition. You are not adding carry immediately. You save them. Okay, and finally you add. And you can show that mathematically that doing so by delaying the addition of carry bits, ultimately you get the same thing, You get the same final sum anyway, right? And I have chosen 3 numbers together because I know that in a full adder block, a full adder block can process 3 inputs together simultaneously, right? Two bits and one. There are 3 inputs, right? So that's why I have chosen. So I have here 4 full adder block, but they are operating independently. There is no signal flow. So they are producing some bits and carry bits independently. I'm saving these carry bits to be used later, and I use the same principle, adding three numbers together and generating the carry and sum bits and carry bits separately, and finally combining them together. So I want to reflect this in hardware now and see whether there is an improvement in time. Okay, and this is what is called carry save addition. Okay, so this is how the signal flows. I mean the data flows. So you have the sum bit and carry sum vector and the carry vector. Then you take these 2 vectors and take one of the sum vectors again here, add them together, and produce the sum and carry separately, and keep on doing this until everything is exhausted. Okay. Final sum is the same, of course. And this is called what is the carry save adder, addition of multiple operands. Let me give you an example here. Suppose you are given 4 integers a, b, e, f, and each of them is 4-bit wide for simplicity. So if I have a traditional adder, what I would have done, now both a and b, they comprise 4-bit each. So this is a 4-bit adder. This is a traditional adder. It may be ripple carry or whatever, doesn't matter. So I add 2 numbers a and b. These are multi-bits, multi-bit numbers. And once this addition is performed, I again add the 3rd number and then the 4th number, right, and get the sum here. So this is the typical traditional approach. I mean, using 2-bit, using 2 input. I mean, using 2 operand adder. But instead, here notice that if this traditional adder is implemented in ripple carry adder, the signal flows sequentially here, and then again through sequentially here, right? Through sequentially here and so on. Let us expand this. So this is a 4-bit adder, right? So this will look like this. We assume that this traditional adder has been implemented using this ripple carry adder, the most simple way formula. So for this, we have an serial interconnection of 4 adders, and they are accepting this A inputs and B inputs bit by bit. So it's a 4-bit integer, so I have 4 copies of full adder. They are connected in series, right? And each of this block produces 2 outputs, right? Sum output and carry output. Okay, so you pass one output here, another output here. And similarly, this is also traditional adder. Again, a 4-bit ripple carry adder. But this time this accepts newer inputs like this like E0, E1, E2, E3. And the 3rd stage, it receives the 4th input, the 4th vector, F0, F1, F, so on. And this carry bits propagates from one stage to the next stage, And finally, see this outgoing carries, they have to be added up here. And then it generates this sum bits. For the time being, let us assume that we are considering unsigned addition. So that's why the issue of overflow and etc. that is not bothering us. Right? So if I have to use four numbers, each of them 4-bit wide, and if I use the traditional ladder, this is how I should interconnect the whole thing, right? Is this architecture okay? It's same, I mean, just replacing each traditional ladder by a ripple carry adder and interconnecting this sum and carry lines, carry bits accordingly to the next stage and so on. So this overall circuit receives 16 inputs from A to F because each of them is a 4-bit vector. So it receives 16 inputs, right? And produces these outputs. So what is the delay? What is the critical path? Assume that each full adder block has unit delay.
So one thing, sir. So when we are adding on the first layer, the output is the sum and the I mean the sum and the carry go from the same line. I can see only one output.
No, there are two outputs, right?
Yes, but line is only one.
Wait, no, one output goes here, other output goes here.
Okay.
One output goes here, other output goes here. All the outputs are saturated, right? Everything has to be added finally, the signals must go somewhere, either to there or to the next stage, either to the left or to bottom. So what is the delay? This is nothing but, I mean, every traditional adder is being replaced by a ripple carry adder and the connections are set this way so that it can receive newer inputs at every stage. Straightaway implementation of this block diagram. So what is the worst case delay? Assume that each full adder block has unit delay.
7.
Yes, 7, because see, look at the signal flow, it vertically down and then straight horizontal, right? Across the horizontal direction. So 1, 2, 3, 4, 5, 6, 7. Delay is added horizontally as well as vertically. That's how this is interconnected. Here, what you are doing, say, whenever you have a generation of carry, you are reusing it to the next stage, right? Whenever there is a generation of carry, you are reusing to the next stage. So this is not carry save addition. This is the classical traditional addition. In carry save, as we explained in the previous example, the carry is not being added. The sum bit and carry bit, they are generated independently. There is no signal flow across the blocks lying in and belonging to the same adder. So what I'm going to do is to let us try to implement the idea of carry save addition in hardware. So what would be, I'm going to change my signal lines then. So in carry save addition, I'm not going to have this horizontal signal lines, correct? Because the carry is not being propagated to the next stage. It is being saved for use for subsequent use, right? So I'm trying to design my hardware in such a way which reflects the idea of carry save addition. Okay, let us look into this diagram. Here, as before, so I have these 4 full adder blocks, but now notice that they are now operating independently. There is no horizontal signal flow. Can you see it? And as I said that each full adder block can process 3 independent inputs. So here, notice that only A and B, they feed this first line of adders, right? Here, 3 inputs feed. You know, this like B, E, and F. Okay, so there are 3 vectors which are feeding this. And there is no signal flow horizontally. The carry which is being generated, same means it is being subsequently used at later stages. See this, the interconnection lines, that is changed. Also this input configuration is a little bit changed. So we claim that this will also generate the same value, because everything is here. You know, I mean, all the carry and some bits, they are already finally being collected here in the last stage. Let us assume that the last stage, that has to be a traditional adder, you know, maybe ripple carry or whatever. But if you look into here, this vertical delay possibly we have reduced. So previously the delay was 7, now delay was what? Is the delay reduced little bit?
6, it's 6.
6, okay. So now you do one thing. So you have this this ripple carry adder. You can replace this by some other carry look ahead or whatever. Huh? So what would be the cost and delay of this thing? And this could have been made a carry look ahead, right? So as you can see, if I am going to add 4 integers here, right? So if we have multiple integers, in all these previous stages, there is no signal flow horizontally, right? They are operating independently, as you can see. Not exactly independently, because they have to wait for these vertical signals to some extent. And this finally, you know, that can be further accelerated using a better architecture here. So this is the basic idea of carry save addition. So you see that you might argue, well, the saving in delay is not significant right now. Isn't so? Previously it was 7 only. Now it has become only 6. Just savings of 1 unit, not significant. But can you do better? That is the question. What do you observe here? So you assume that this is a logic block. So this logic block accepts 3 inputs, produces 2 outputs, and then another logic block, it receives a new input here. Okay. Each logic block receives 3 inputs. And why 3? That we have discussed before. And again, you know, it generates 2 outputs. And if I have multiple inputs, A, B, C, D, etc., you know, at each level, I'm going to add a new input, right? So just look into this diagram and you tell me, can you do better? How does it look like? This isn't it a serial chain? I mean, this is a block and then new input appears and then another new input appear here. So it's like a chain, right? So whenever you have a chain of signal flow, can you do it better to process the newer inputs?
So carry look ahead.
The carry look ahead is for the to expedite the last stage, you know. But can I change this? This is a linear chain, right? Because at each level you are processing a newer input.
The prefix sum.
Not prefix, but just imagine that. So, I mean, what is
Just a
the
simple binary tree.
right? It's not binary because it has three inputs, right? So yes, we will be constructing a tree. This is a chain. This is a serial chain. So we will transform the chain to a tree. But this tree has three inputs, as you can see, right? Slightly different type of tree. Yes, you are right. Because as it is serial, that's why the depth increases, right? And that gives you the vertical, this diagonal delay here. So I want to reduce this diagonal delay by changing this serial structure to a tree. And I will reduce this horizontal delay by changing this ripple curry architecture to CLA or by prefix tree or something like that. So I'm going to do two modifications here. Again, using the simple concept of like trees and everything, right? Which is abundantly used in computer science. So this is what you have seen so far. So assume that you have n-bit numbers and I have m of them. So here x0, x1, it means that each x is a vector, you know, with n. So this is my logic block which accepts three inputs. I mean, these are actually buses, you know, anyway. And then at each level you process one new input, right? So therefore you have a chain here, you know. And that's what in the previous structure we had similar things, right? And that's why this vertical delay is caused. But instead, as you said that, well, I have this n inputs, m inputs. I am taking three of them together and trying to make this tree. I group them three, and then each of them produce two outputs. And again, I make groups of three and keep on doing this, right? So what is the depth here? And what is the depth here? The three inputs that is being compressed into two outputs, right? So the depth is log of m. There are m leaf nodes. And each level, three inputs are being reduced to two, right? So this base would be 3 by 2. Here,
So
if we
what if our like we don't have our inputs as multiples of 9? So like we have 7 or 11 or 13 numbers we want to add.
say it again.
So like for this tree to work, we need to have 9 inputs or 18 inputs or things in multiples of 9, right?
Well, not necessarily. If it is not multiple, you can assume that those inputs are 0.
Okay, sir.
Yeah, just set them to 0, doesn't matter, right? Okay, but the idea is, you know, if you connect them, so this is some kind of serial connection, and that's why the delay becomes of the order of m, right? Vertical delay becomes of the order of m, and the final stage, which is here, is called LCA. LCA is nothing but CLT, and so here is the logarithmic delay, and so is the log of n plus m, and the vertical delay is m. And if you change this to this one, this compressing, you know, three inputs to two outputs, and so you have an underlying tree here. So therefore, this depth reduces to logarithm of L, right? So this is called the Wallace tree architecture for adding multiple operands with carry save addition. So because of this architecture, the depth becomes log of m. In fact, this base is 3 by 2. That's not explicitly written here, and this term remains the same. Only thing that here you have m, but this becomes log of m because the depth is log of m. And this part you can accelerate using CLT or whatever. Okay. Again, looking back into this architecture, compared to the traditional architecture, you can see that by grouping these inputs appropriately, And organizing this adder in a tree fashion, we can do much better in terms of the total delay needed for adding multiple numbers. And these are called carry save addition, and this tree architecture in particular is called Wallace tree. There are other tree architectures known as Dada tree and so on. You may look into the literature for further information. Well, so that's all about integer addition. Any comments so far? So what did you study so far? I mean, let us summarize. We started with ripple carry adder, and then we thought about carry look ahead. We identified the carry recurrence relationship, and using that and that enables us to write the Boolean expression for the carry signals in terms of inputs, G's and P's, and then following those Boolean equations, we can design our hardware accordingly, but that becomes expensive. Then we thought about improving the cost of the architecture. One of them was to consider hybrid structure, like combining ripple carry and carry look ahead together in different form. And then we talked about carry look ahead tree concerning, I mean, that carry look ahead architecture in multiple levels, which gives rise to carry look ahead tree. And next we studied the theory of prefix trees, and we saw that there is a fundamental problem hidden in the entire carry generation process, which can be abstracted as the computation of the prefix sum or prefix product computation. And we have nice trees that enables us to compute that with reasonable amount of delay, cost, and fan out. And we studied different ramifications and different improvement. And instead of looking ahead of carry, we also have a mechanism of looking ahead of sum. This is called carry select adder. And finally, we studied addition of multiple numbers, and that led to the concept of carry save addition, right? So that's the whole summary of addition so far. Is that okay, right? So now let us move to integer multiplication and see what sort of mechanism or what sort of hardware solutions we have we can use in practice. So in a multiplication, you have what is called the multiplicand and multiplier. You have two numbers you want to multiply, right? And then we have the concept of partial product and final sum, right? But the advantage is we only have zeros and one in integer in Boolean space. In digital space, we have only zeros and one. So this partial product is very simple. So consider two binary numbers. Let us assume for the time being that these are unsigned numbers. So how do I multiply? I look into this term, and if it is 1, I just copy this, right? And then I move to the next bit. And so happens that this is 0. So everything would be 0 here, but just 1 plus shifted. So it's the same algorithm which we follow in our just school level multiplication, but in terms of only zeros and 1, and that makes our life simple. If it is 1, you just copy this. If it is 0, you just copy all zeros. And this entire vector is shifted by 1 bit at every stage, right? That's it, right? And then keep on adding. So these terms are called the partial product because you are taking the product of this, right? So if you consider the unsigned number, this represents what? Plus 8, right? And this represents plus 5. I mean, unsigned, I mean, everything is, you may assume that it's positive, just the absolute value. So this is 8 and this is 5, and what about this? Is this 40? Right? This is 32, this is 8, this is 40, right? So the product is correct. So this term, this one is called the multiplier, and this is called the, sorry, this is called the multiplicand, and this is called the multiplier. I mean, they can be used interchangeably, of course. So you tell me in hardware, then what I have to do? Suppose you are given these two strings as input, and I want to produce this. What would be the hardware solution for implementing this? Based on whatever you have studied so far. How do I generate the partial product?
So if that digit is 0, then it's 0. If it's 1, it's just the multiplicand, but shifted that many positions.
That means in logical terms, what operation you are doing?
Right, left shifting.
No, logic operation. And or etc. Between two bits.
And.
Yes, simple and, Say you are taking and of these two bits, getting 0. You are taking and of this one and this, you get 0 here, right? Similarly, you are taking and of this and this, you get 0. You are taking and of these two ones, you get 1 here, right? So bit by bit and nothing else. Is it so? And the next one, you just consider the next bit and the same bit by bit and, right? Just shifting one place. So all you need is nothing but an array of AND gates to generate this bit by bit AND product, right? And you need some kind of this shift mechanism. And then you have these numbers, right? You have so many rows, depending on how many bits are there in the multiplier. So each of them is a binary number. So you are adding multiple numbers, right? You are adding multiple operands. So what can you think of? Addition of multiple operands.
With carry save adder.
Yes, we have just studied that, right? So see, this carry save addition has a direct application here now. Because unless you do carry save addition, then adding this partial product, would cause a long delay, right? Because there may be many rows here depending on the size of the multiplier or the multiplicand. If there are more bits here, there will be many rows here. This matrix will become larger. See, that's why you see you now see a more important purpose of the carry save addition. Is it so? So all we need is some array of AND gates to create this partial product, and then some sort of carry save addition to create this, to produce the sum. Done. Right? Okay, now let's do one thing. So far, we have assumed that these are unsigned numbers, just absolute value, right? So this represents 8, this represents plus, and we have just done bit by bit ANDing and just and then we have summed them following the usual rule, and I get this result. And this is indeed 40. Okay, this contributes 32, this contributes 8. So this is 40, and which is supposed to be. This is correct result, right? Now suppose this has a 2's complement number, you know. So then this becomes a negative number, right? And this becomes a positive number. Okay, okay, we discuss that a little bit later. So assume that it is 2's complement now. So in 2's complement, 1 0 0 0 is what? Is minus 8 in 4-bit 2's complement, and this is plus 5. So the result should be minus 40, right? But I have resolved this one, but this is the result is plus here. The result is plus 40. So it fails for 2's complement. The same example shows that. Another thing you might observe that suppose I have a 4-bit and 4-bit, the total product may be of 8-bit long, because the size of the number increases. So that's why, you know, if you have 32-bit, if you multiply two 32-bit number, the result would be 64-bit. In MIPS, you have seen this kind of thing, right? When you have multiplied two numbers, the result should be stored in a 64-bit register. I mean, two registers, high and low. That's because that log of NM is log M, log N plus log M. So we have observed many things from this simple table, that multiplication involves computation of the partial sum. That is nothing but computing AND operation bit by bit. And then we need to add all this partial sum, which boils down to the same problem as carry save addition. And we observe that the final result would be, the size of the final result would be twice as long as the input size. And the simple procedure of computing multiplication may not be valid for 2's complement number. So these are the 4 observations we have made here, right? So we also notice that this is nothing but, this boils down to the carry save addition, because as we need to add multiple numbers. Okay. So now let us think about in terms of hardware. How should I implement this, and what should be my hardware architecture? Finally, you have to add bit by bit anyway, right? So I need full adder blocks and so on. So basic blocks we need, but how do I organize them? And I need to organize this AND gates also for computing this partial product of pairs. So I need an array of AND gates, an array of full adder blocks, and interconnecting them appropriately, so that the resultant product is produced at the output. Right? Let us see that how should I map it into hardware. Okay, carry save, we just studied carry save, and we have noticed that use of carry save addition would expedite the computation time here, the multiplication time. So let us look into the unsigned multiplication. And in general, let's say that we have the A's and B's, all these are binary bits, 0, 1, 2, 3, and B also runs from 0, 1, 2, 3. And we are adding 2 4-bit numbers, right? So A's and B's are all 0s and 1. And so we get this partial product. This partial product is the ANDing of these 2 bits, A0, B0. Next, this one would be what? Is A1 and B0, right? And this would be A2 and B0, and A3 and B0, right? And similarly, I shift this one cell to the left and keep on doing this. B1 A0, B1 A1, and so on. So that means I need AND gates. Suppose I want to generate all of them in parallel. I need so many AND gates and feed them appropriately with these inputs so that they will generate all these bits instantaneously. I mean, after unit logic delay. And when you multiply n-bit number by an n-bit number, it gives an n plus n-bit result. So this is the general view of the whole thing, and we want to now map it into hardware. So of course, needless to say that it is more complicated than addition, and it's accomplished by array multipliers. Array means, since you have to compute the partial product, we need an array of AND gates. So that's why it's called array multiplier. There is another possibility, which is the shift and repeated addition. I can keep on shifting and adding it recursive, one by one, sequentially. So, and obviously, it would take more time and more area in hardware than the addition operation. And we will be using these two terms, multiplicand and multiplier. The first one is called the multiplier, which you normally write at the top, and the number which you write at the bottom is called the multiplier. And keep on doing this. For negative numbers, it is better that you assume that both are positive. I mean, both are absolute value, and then compute the final result and then just adjust the sign. That's much simpler, right? Or maybe you can use other techniques like Booth algorithm that we'll study later on. Okay, so let us first look into this one hardware solution. We have this multiplicand here. So let us say x0, x1, x3, x2, and multiplier is y0, and these are the partial product terms, right? So what could be the overall hardware? So as we have noticed that all we need we need AND gates, and then we need additional, we need AND gates, and then we need these vertical adders, right? I mean, the adders which can perform vertical, I mean, the numbers appearing in the columns, the bits are appearing in the columns. And then those carries need to be propagated from left to right, from right to left, right? So what could be the overall design of this? Simple design of multiplier. For the timing, forget about the cost and delay and so on. Just think of, you have an array of AND gates, and then you have an array of full adder blocks. They are adding these numbers along the columns and propagating the carry to the left. Okay, so let me show you the overall diagram, and then you would be able to see that it is obvious, Okay, so this is the vector y0, I mean, so if you look into the first row, everything is being multiplied by y0, right? So that's why in hardware you take this line y0, which fans out, and you take these bits x0, x1, x2, x3. So you have a small AND gate here, x0, x1, x2, and x3, and this y0 feeds to all of them. So that means these AND gates will generate these values. And similarly, you have this next layer of AND gates, which is fed with y1, because if you look into this row, this y1 is common here, right? So take y1, and it is being multiplied by the same vector, x0, x1, x2, x3. So they are generating this partial product, and then you use this array of full adder blocks. Some of them may be half adder, doesn't matter. And keep on doing this. Just emulate this, Whatever you see here, that's being reflected in the hardware, nothing else. And these full adder blocks, they represent the ripple carry, as you can see. And the final carry is being propagated to the next layer of adders and so on. and you get the final output through as the output here, right? So there is the, I mean, if you just look into this, the partial product, the array of partial product, and look into the diagram, this is straightforward. All you need is an array of AND gates, feed them appropriately. So that it looks nice, I mean, there's not much crossover of wires. And arrange the adder blocks accordingly, so that this addition is performed. Okay. So as before, see there is a horizontal flow of signal as well as vertical flow of signal, and thereby this is the critical path. See, maybe the longest path. So if I have n by n, so then I have to traverse all the bits in the multiplier as well as all the bits in the multiplicand. That's why the propagation delay is twice of the order of, is twice of n. So do you follow it?
Yes.
I think so. Yes, I think so far it's the architecture is simple. It is a straightforward reflection of this, whatever you've seen here, right? And this interconnection among the full adder blocks is self-evident, because say you have for each block, from each block there are two outputs, right? So you have to utilize those two outputs accordingly. So one goes to the left, one goes to down, so that all the signals are collected, finally, to generate the final output here. So this is called the conventional array multiplier using ripple carry adder. Simple to implement, but I mean, the cost is, of course, this is quadratic, because it must be n times n, right? Because this is a two-dimensional architecture. So n by n. So many full adder blocks you need, quadratic, and also this quadratic number of AND gates. So cost is quadratic, delay is linear. So what would be our improvement next? I think I will stop today here, because there are too much stuff, But just one last question: what would be the next possible improvement? So here you don't see the application of carry save addition, right? It is straightforward implementation. If we just look into this portion, you are adding multiple numbers, right? Although the numbers are a little bit shifted, but that doesn't matter. You may imagine that there are zero padded here. So you are adding multiple numbers. So it's the entire architecture here that can be replaced by the architecture for the carry save adder, right? Which would improve this, the worst case delay. So that we will discuss next time. So let me stop here today. I think we have discussed too many things. You have any comments or doubt so far? Any question, comment?